Here I'm going to talk about the remainder theorem. The remainder theorem basically allows us to find, for example, here, p of 5 using division. Now, you might say, well, I can just plug that in. Well, as polynomials get bigger, you might not want to, and this, has some cool applications. It's just a nice little shortcut. Now, one of the things that I find useful in examples like this is to break it down to something that's a little simpler. So let's say we have 23 divided by 5. So this is going to be the same concept. We know that that is just equal to 4 remainder 3, right? 4 with a remainder of 3. Well, what that means really is that 23 is just equal to 5 times 4 plus the remainder 3. Again, that's kind of what division is. So if that's the case, let's go ahead and just label these with their names. All right, so I've got my dividend, my divisor, my quotient, and my remainder. Well, what we're going to do now is we're going to set up our equation, or we're going to set up a division problem that allows us to relate the dividend to the remainder. Okay, so in this case, what we're going to do is we're going to take p of x, and well, this is basically saying, I'm going to call it a, that a is equal to 5 here. So I'm going to divide by kind of working backward and kind of getting a factor from that. I just did air quotes. You probably couldn't see that. And we're going to have x minus 5, or really x minus a in this case. Okay. So we're going to divide by x minus a, or x minus 5. So I'm going to write that all in kind of its general form over here. And then the quotient, well, I don't have that yet. But I'm going to go ahead and just call that q of x. And then the remainder I'll call r of x. Now, what I'm trying to illustrate here is in this particular problem, based off what I have here and kind of how I defined what I'm looking for, well, x is equal to 5. So in other words, what I end up here is that x and a are the same thing. They're equivalent. So I just basically get x minus x here, which is of course going to end up just being 0. Now everything else kind of remained the same through those steps. So I'm going to just do some shorthand here. And what we're going to see is that by basically making sure that x and a are the same, we have now set up our equation to where whatever p of x is the same as our remainder. Now, that is a little abstract, so let's look at our example here. In our example, we had that a was equal to 5 and x was equal to 5. So let's go ahead and plug everything in here. So now if we want to find p of 5, well, then I know that that's just equal to x minus a, which in this case, both a and x are 5, so that's easy. It's just 5 minus 5, and we're going to see that 0 that we wanted. And then q of 5, the quotient when x is 5, which I don't know, but we're going to find I really don't care either, plus the remainder when x is 5. Oh, well, that just leaves me with a big fat 0 right here. 5 minus 5 is 0 times anything is just going to give me a 0 plus r of 5. So p of 5 is just going to equal r of 5. Oh, well, cool. If that's the case, then if I want to find p of 5, I just need to divide p of x by x minus 5. And that will give me what I was looking for. So showing the synthetic division here, if I go divide 5, again, using my a value there, or the 0 of the denominator, okay, and then I have my coefficients of 1, 3, and positive 2, and then we just go through our process here, and again, the only thing I care about is my remainder. And if you want, or just to show you, if we were to just plug it in the way we normally would, we'll get the same result. Now, as you can see, even in this case, this way is going to be a lot faster. So if you ever want to find what the output will be given an input, you can just divide using synthetic division and look at the remainder, and it'll get you there.